Day 22 of 30-day lead coding challenge, and the problem is to find the count of all the subarrays whose sum is equal to a given number k, and it's lead code problem number 560. So we will see the solution and then also the code in C++, Java and Python. So there are multiple versions of this problem. One is that you are not allowed, there are no negative numbers in the array. So there the solution is slightly easier. Here you are allowed to have positive as well as negative numbers or zero in the array. So this is the version which has negative numbers, which can have negative as well as positive numbers, both mixed. For example, in this array, and you have to find how many subarrays have a count of, let's say, 2. So let's first do it manually. So we see that this is 1. Then if we include these two, it's 1, 0. Then if we include these 3, we get 2. That is 1, 0, 1. And we can store the index, that is 0 to 2. Then are there other possibilities? So 2 itself can be a subarray with just one element. So next is 2. Then you see that this is 1, this is minus 1. So if I take this part, that is 1, 2, minus 1, then its sum is also 2. And sub-array means it should be contiguous, you cannot skip any element and in the same order. And then we have got 3. Are there any other numbers? So we had seen this to this, but if I include 0 here, that does not change anything. The sum still remains 2. So this is also a subarray. So next is 0, 1, 2, minus 1. Are there any other subarrays whose sum is equal to 2? No, that doesn't look like. So for this case, our solution should return 4. And now how we will solve this problem? If it was, suppose it was completely positive numbers, then what we would have done, we would have started here and we see if the sum is more than k or less than k. If it's more than k, then you have to eliminate some numbers, and you can eliminate from left and right. But let's say you are scanning the array from left to right. So if you shrink the array from right, then you go back to previous step. In the previous step, you were at this position, you came here, you found that the running sum is more than k, so you want to shrink your array. So if you shrink from right, you go back to where you were. So again, it's guaranteed that the sum will be less than k, because that was the region you included the next element in the first place. So you will shrink from left and expand in the right. If it's the running sum of a given subarray is less than k, you will include next element. If it's still less than k, you will include one more element. And including element will only increase your sum, because we are talking about the case where only positive numbers or 0 are there. But let's say including the next number, the sum becomes more than k. Earlier it was less than k. So you have to decrease. So you will decrease from left and again compare. But that is not the case here. I'm just giving you a intuition how you would have solved it if all the elements were positive. So here we can have negative as well. So one thing to note is that no matter what is the subarray, let's take this subarray. This ends here at index 2. This subarray ends at index 3. This at 4 and this also at 4. So no matter what is the subarray, it will end somewhere. And we will try to find all the subarrays ending at a given index by scanning from left to right. We will scan the array from left to right once, and when we are at a given index, let's say here, then we will figure out how many subarrays ending at this current index have a sum equal to k, and we will keep incrementing our count. So we initialize our count to 0 before starting the scan. And how we will know that? Let's say this is the subarray from 2 to 4. Let's say we are talking about this subarray. and this we will figure out when we reach 4. And let's talk this case. So here the sum is 2. Sum is 2. And when we are scanning from left to right, we will keep track of a running sum, current sum, which will be sum from beginning till current index. So when we are at here, it will be 1. When we come here, it will be again 1 because we added 0. When we come here, it will be 2. All the sum from beginning till here. And similarly, here it will be 4. Here it will be 3. So this is the running sum when we are doing a scan from left to right. So at each index, we check if the subarray ends here, then it will begin somewhere. So in this case, it begins here. So how we will make sure that we have a subarray ending at here, whose count is k. So we have to eliminate the subarray before it. Let's take a more generic example. Let's say we have array A, B, C, D, E, F, and we are at index E. And let's say this is the actual subarray whose value is equal to k. So now what is this value? This value is current sum. And this value from here to here, it's k. So what will be this value? This will be current sum minus k. But when we had started scanning and we had reached at B, we would have found this CS minus k. So what we will do, at any index, whatever is the value, the current sum, we insert in a map. So we have a map where we keep inserting current sum along with how many times it has occurred. Because it can occur multiple times. So let's say 1, 2. So 3. 3 was not there in the map. So we store 3 equal to 1 count. Then we have a 0. So again we have sum from here to here is 3. So we store that there are 2 subarrays whose sum is 3. So that's why we will keep track of count. So the first time we visited we would have already stored this value in the map. So when we are here, we will check if CS minus k exists in the map. Then that means that k, there will be subarray ending at current index whose sum will be k due to this logic. If this sum exists, then this has to be k because this is CS minus k and this is CS. This we know when we are reaching here. So k also exists. So that will be the approach. So let's run through this example. So we come here. Our current sum becomes 1. We see that is 1 in the map? No. So we store 1 with a count of 1. Then we come here. Current sum is again 1. So we see if current sum is there in the map. Yes. So we make it 2, increment its count. And we also check if current sum minus k exists in the map. Because if current sum minus k exists in the map, there is a subarray from 0 to some index whose value was this. So we will subtract that prefix. So we are storing the sums of prefixes, not subarrays here, but prefixes. So if a prefix exists, by removing which I can get k. This is the sum of this prefix is CS. The sum of some other prefix is CS minus k. So if I chop out this prefix, I get a subarray whose sum is k. So if CS minus k exists, we will increment our count. Count plus equal to this map CS minus K. Maybe this 2 prefix sums to CS minus K. There is 1 0 which also sums to CS minus K. So all of these uh, will will be part of our result. For example, here you saw that 1 2 minus 1 was part of the result, and this 0 1 2 minus 1 was also part of the result. So this is the thing we will do. So here 1 minus K is minus 1. Minus 1 does not exist in the map. So we'll move ahead. And where is the map? Map is here. And we come here. The running sum becomes 2. So we see straight away that 2 is equal to K. So we increment count to 1. So count becomes 1 now. And we also check if CS minus K exists. So 0 does not exist. And we also insert the CS into the map. So now 2 is inserted with a count of 1. Then we come here. We see that running sum is 4. Is it equal to K? No. Is CS minus K present in the map? So 4 minus 2 is 2. So is 2 present in the map? Yes. There is a 1. Count is 1. So we will increment it by 1. And what that will denote? 2 was the sum from here to here. So we have to subtract this part. So if you see, if in this we subtract this part, whose sum was 2, then we get a subarray, which will be 2. So we got this answer. Earlier we had got this one. So these two we have got here, and count is 2. And 4 we will store in the map. And then we come here. We see 3. 3 is not equal to K. Then we check if 3 minus 2, 3 minus K is in the map. 1, yes, there are 2 subarrays. There are 2 prefixes whose sum is 1. So we increment the count by 2. And what are those prefixes? This alone and these 2. So we will remove these 2 prefixes from this entire thing. So when we remove just 1, we will get 0, 1, 2 minus 1, this one. And when we remove the other prefix whose sum was 1, we get 1, 2 minus 1, that is this one. And we also store 3 in the map with a count of 1. And now we have reached the end. So we will return the count, which will be 4. So I hope you understood this problem. Now let's start coding it. This is the problem. It's explained with an even simpler example. I took a more generic case where I added some negative numbers as well. And first we will write it in C++, then we will modify it to Java and Python. So if it's an empty array, if nums.size equal to 0, then we return 0. Else we will keep track of count equal to 0. Then we will have unordered map int. Let's call it map. And here the value denotes prefix sum and count. How many prefixes have that same sum. And then the running sum. Or here we will not need this index also, so we can directly iterate like this. So if we found a prefix by removing which I can get k, then I will increment the count by that much. And now we have to add this key, this prefix sum. This is also a prefix sum from 0 till current index. So if it exists in the map, we will increment the count. If it doesn't, we will insert it. So if map dot find current sum not equal to map dot end, that means it is present. So we will have map current sum plus equal to 1. Else, if it's equal to end, that is reaches end and did not find this value, then we have to insert it. To insert it and add a value of 1. And now this loop will end, and finally we will return count. So let's run it. And this passes this test case. Let's add our own test case. It was 101, 2 minus 1. 1, 0, 1, 2, minus 1, and k was also 2. So let's see what this solution gives. So it says 4, and we had seen in our explanation also that there are 4 such subarrays, and these are the subarrays. We need to return the count only. So looks like it should work for all the cases. So we should submit it. And this solution is accepted. So we will modify it for Java now. First, let's copy it. So its length and it should be hash map integer then this will remain same, and instead of find we will check contains key. In fact, C++ also has this contains in the map, but it's in C++ 20, so still not available. So in C++ we need to use this not equal to end thing. So if contains key, we increment count again. And rest. So if it contains, then we will get it first and then replace that. So into val equal to map dot get current sum, and here also I think this will not work. And we will increment it by 1. So this is the new value that will be replaced. and this seems to work. So let's go ahead and submit. And the solution in Java is accepted. So let's write in Python. Let me copy it. It should be len. If current sum minus k in map, so this key is in the map, so we increment the count by this much. Let's try. And it compiles. So it should also accept the solution. What is wrong here? Why is it giving 0? Okay, so here we missed this 0. So if it's of some length, it's straight away returning 0 here in the beginning itself. It's not processed at all. Now it looks like it's correct. So let's submit. And this solution is also accepted.